In this video, we're going to solve the ALEKS problem called Understanding that Electrostatic Forces Add as Vectors. This problem is going to give you a graphic. There's going to be 3 charges inside the graphic. One of the charges is going to be highlighted with a little green ring around it. I'm going to highlight it even more to make it easier for us to see. The other, I've flipped through a lot of versions of this problem. The other 2 charges, the ones that are not highlighted, they are always going to be the same magnitude. They may not be the same sign, like in my problem, one of them is +2 and the other is -2, but they're always going to be the same magnitude, meaning that they're going to have the same number. Also, the other 2 charges are always going to be the same distance from the highlighted charge. They might not be in this exact same arrangement. They might be kind of lined up like this or some other pattern, but the magnitude of these 2 charges will always be the same. Will be different from, it might be different from this one, but these 2 will have the same magnitude charge, and they will also have the same distance to that highlighted charge. So our job is to figure out what the net force is on that highlighted charge. If there is no net force on the highlighted charge, then we're just going to select this bubble in the middle that indicates no forces on it at all. If there is a net force on this highlighted charge, we have to figure out what is the direction of that net force and choose the correct arrow. So to help us solve this problem, we're going to keep in mind that like charges, so things that have the same charge, either both positive or both negative, like charges are going to repel each other, and opposite charges are going to attract each other. And since our charges are going to have the same magnitude, and they are also going to have the same distance to that highlighted charge, the magnitude of the charges are going to be exactly the same, or the magnitude of the forces are going to be exactly the same. We're just going to be using this concept to help us determine if these charges are being pulled towards each other or if these charges are being pushed apart from each other. And the same down here, are they being pulled together or are they being pushed apart? So these 2 charges, because they are like, they're both negatively charged particles, these 2 charges are going to be pushing each other apart. For now, we're not even thinking about this guy over here. Ignore it completely. Because these are both negatively charged particles, they are going to be repelling each other, and these 2 particles right here are going to have an effect that would push that -3 charge in the downward direction, just like that. And again, we're not paying attention to this guy. We're just thinking about what's going on right here. This charge would also be pushed away, but remember, we're only focusing on the -3 charge. Now we're going to think about these 2, and we're going to ignore this one completely. Don't pay attention to it at all. Because these are opposite charges, they are going to attract each other. So they're going to be pulled in this direction, and that's going to give us a movement like this. So this particle right here is going to experience some movement in the direction to the left, and it's also going to experience some movement in the downward direction. Both of those motions taken together are going to give it sort of a downward and to the right motion. So we're going to choose not this arrow because that represents only the motion due to the +2 charge. We're also going to not choose this arrow because it represents only the motion due to the -2 charge. We're going to see something in the middle, motion in the middle. So if you had a scenario where one charge was pushing it to the left and the other charge was pushing it to the right, that would be a scenario where you would choose that bubble in the middle, indicating that there is no net charge at all, or no net movement at all.